Welcome to the Compendium of Knowledge, a living library of ideas, values, and insights meant to spark curiosity, open our minds, and help us see the world with greater depth and humanity. Today, we are honored to be joined by Dr. Morten Peter Meldal, who won the 2022 Nobel Prize in Chemistry. Dr. Meldal is known for helping create click chemistry, a way of joining small chemical pieces together quickly and precisely, like snapping Lego blocks into place. Instead of slow and messy reactions, scientists can now build complex molecules in a clean and reliable way. This has helped make medicines faster to develop, materials stronger and smarter, and biological research easier and more accurate. Today, Dr. Meldal is a professor at the University of Copenhagen, where he continues to show how simple ideas in chemistry can lead to powerful, real impact. Dr. Meldal, it is an honor to welcome you to the Compendium of Knowledge.
Thank you for having me.
So firstly, for a young audience, could you explain in simple terms what you discovered that led to your Nobel Prize, and why that discovery changed the way scientists make and use molecules?
Yeah, first of all, the discovery was really quite serendipitous, and as most discoveries actually are. Because if it was something that we knew already, something that was in the books, sort of, then you would not be discover a new thing that would be useful for everyone. So we were working on something entirely different actually at the time, trying to make a lot of different organic chemistry reactions on what is called solid support, that small plastic beads that we use for the synthesis. And one of the reactions just didn't want to work. So it was a chemical reaction that just didn't want to work. We were using amino acids which was converted into acids, and we were trying to couple those to alkynes on the solid support. And this just didn't work. For 3 months, a very skilled young PhD student that worked with me tried to make this reaction happen, and after 3 months he came to me and he said, Professor Meldal, I think I should rather work in the industry because this is not really me. And then I asked him what it was, and we looked into it, and we found that this new reaction happened that nobody has seen before. So we follow up on that, and he did a lot of experiments over the coming year, the next year, and then he went to the US and presented this at the APS in San Diego. And this was the start of a very long and a very successful development of this chemistry, where a lot of people around the world has contributed. But it eventually ended up being a Nobel Prize because of the this reaction can happen in the presence of any other chemistry, and this is what makes it so unique. It's completely selective, and it works all the time, independent of what conditions you take it under. It still works. So that is why it has become so mainstream and used so much in medicinal chemistry, in materials, as you said, also in nanochemistry, to make new materials and surfaces and so on.
Thank you, that's very interesting. And I find it even more interesting that many laureates who I've interviewed, they've said that their discovery, as you said, was actually somewhat of a coincidence and not something that they have been actively searching for.
Yeah.
And yeah.
But that makes sense, because if it was something that was straightforward, it would already have been done. There are so many people working on research around the world, and if it's straightforward, people would have done it already. But what is so critical is that you have your eyes open, that you are actually primed for the discovery, that you have an intuition and an idea that you don't know everything already, and that you are actually capable of seeing that here something new is happening, rather than throwing your experiment into the waste. You follow up on the discovery that you make, the observation that you make, that something is not fitting into our concepts.
That's very interesting, thank you. And your work has showed that chemistry doesn't need to always be slow, complex, or unpredictable, but that molecules can be joined together precisely through what is now called click chemistry. But I wonder, before all this, what originally motivated you to explore chemistry, if not for a Nobel Prize?
I think chemistry is a wonderful discipline. I really like chemistry. I still spend a lot of time in the lab. I've been in the lab all day today, for example. And I think that chemistry is really, somewhere between theory and reality, where there's a playground that connects theory with reality. And we have a saying here that in my laboratory, that if there's too much calculation in it, it's not science. So we need to be able to prove our calculations with scientific experiments. And a lot of science is done by calculation today, and we get better and better at it, but I still think that showing it in reality is very important. Also, the nature is very, very complex. You will see, as I don't know if you know anything about organic chemistry, but as you progress and understand more and more of organic chemistry, it becomes a very diffuse discipline where electrons, you have to know where the electrons are within the molecules and what they do and so on. It's not just learning that reaction and this reaction. It's actually understanding what the electrons are doing. And this is a very, very complex affair in nature. And that leads to eventually biology. And this is why it's so important to have chemistry in your education. Chemistry is really everything, There's nothing around us that is not molecules, that is not chemistry, that interact with other chemistries. So even if we have a feeling, or we feel hungry or tired, that's chemistry that actually is at work. It's compounds that goes into receptors and trigger these feelings for you.
That's so true. It's about learning about the world around you, not necessarily chemistry. But I'm wondering, at what point in your life did you know that chemistry is something that you want to pursue? And how do you know?
So it started actually when I was very young, like when I was 10 years old. I was at my grandparents' farm on a small island in the Baltic. And I was there all the holidays. My parents sent me over there. And it was fantastic. So I got out at 7 in the morning and came in at 9 at night. And I played around in the wonderful areas of meadows and forest and beaches and so on. And one thing that came to my mind is, what is it that makes this complicated system that is a forest, for example, the trees, the bugs, the flowers and so on, the bees, what is it that makes them communicate? How do they know what each other is doing and where they should go? And of course the answer to that is chemistry. I didn't know at the time, but I was very interested in figuring out what it was that made this whole harmony in the forest. So later on, when I was probably 15, 16 years old, I started doing fireworks. So I went out to a chemical company here in Copenhagen, and I bought a lot of explosives, actually. Brought them home with a train. You can't do that today. And I made the most wonderful rockets and fireworks and all sorts of things. And this was, of course, very exciting at that age. So that also spurred my interest. Then I started as an engineer student, and there I really got a flair for programming. I loved programming. I still do. And I was almost becoming a computer scientist instead of a chemistry scientist. But then I thought about it, and of course chemistry is everything, so that's where you should put your efforts. So I became a chemical engineer, and after that a PhD in chemistry and postdoc in Cambridge and so on. And it was a lot of fun. I've always liked to be in the lab. It's an amazing place.
Thank you. That's a really beautiful story when you were a child. And I'm also wondering, in your entire professional life, if you had to give one lesson, one thing that you think would be most beneficial for the youth of today, what would that lesson be?
So that message today, and I think that's a serious message, is that there's no reality in a mobile phone. The reality is around you, and it's your curiosity for this reality, for knowing this reality and studying it, that makes you become a person with an identity. So I think that you should really focus your attention to the reality around you. You should forge contacts and networks in reality, not on the internet. So meeting other people and talking with them, finding out where do they stand, what are their real feelings. You know, this is very important, but it's also important to dedicate yourself to whatever you're doing. So in order to be a creative person, in order to be a whole person, you need to do what you do with conviction, and it doesn't matter what it is. All professions, all sides of life are important and can sort of benefit from your attention, and you should try to do that, because it's really satisfactory when you do a project, when you make something in reality and you step back and you look at it and this is your project. It's really a proud moment, and it's worthwhile. It really makes life worthwhile to do that.
Thank you so much. That's really powerful. And the part where you spoke about physical relationships, I completely agree. It's something which is almost dying in the world today.
Yeah.
And also, you've previously talked about the importance of introducing chemistry to children at an early age.
Yes.
Why is this something that you have found to be so paramount, so important in today's world?
When a child is born, it has no recollection of anything in this world. So it comes out and it sees a complete chaos, a chaos that is much more complex than any organic chemistry. This chaos, it has to learn to navigate it, and the way it does that is by storing images, situation, abstractions as pictures in the mind. And the children are extremely good at doing that. This is how they learn their language, not by grammar, not by words, but by whole pictures or sentences that sticks to the mind and allow them to speak freely after a few years. If you have to learn your language in the other way, with words and grammar later on, you stay a very poor linguist for quite a while, actually. A lot of accent, a lot of wrongs, and so on. But the children, they float into this without any efforts. And it's the same with their images. They store the images of everything around them to be able to navigate it later on. And therefore, the image capacity of the children is much stronger than grown-ups. And now chemistry is a three-dimensional world. And today, most countries, most places I know of, they start chemistry teaching when you are in the middle of your puberty, where you are actually more emotional than imaginary, have an imagination, rather emotions than imagination. And your capacity to store this as memories is very low at that age. So I think it would be very good to take this three-dimensional world and present it to the children when they still have this capacity of storing images, storing movies, or storing an idea as a picture. And then they can use that later on. I'm pretty sure if we did that and did it with conviction, we could have high school kids at a level of bachelors at the end of their schools, and they would not be pressured. This should be entirely a good experience for them, because it's only when you feel good that you learn something. You cannot learn by force. You can try, you might learn a little bit, but it's when you are going into it with your own will that you really learn something.
Yeah, I completely agree that, I mean, of course, knowledge is really important. The thirst for knowledge is even more important. But I guess, as you were saying, if we are almost giving subjects at such a late age, it's really hard to develop a real ability, a real technical ability in them.
Yeah.
As you did when you were younger. I mean, you had this thirst for chemistry when you were so young, which is probably a big reason why you love it so much.
Yeah.
And also, lastly, my personal impression is that Nobel laureates have always had one thread in common, which is the desire to contribute to something bigger than themselves. Mm-hmm. Now that you have received this recognition, what are you doing to continue inspiring and empowering the youth of today?
So my main legacy is not the Nobel Prize. My main legacy is all the young people who are present in all the bigger companies and academia in Denmark and Europe. And I'm very proud of these students that have gone off from me, finished their studies with me, and gone off to make their own careers and their own history there. And really, I think that not me, but all the education in Denmark has contributed very much to this very strong standing of Denmark. Because I believe that education is the best investment any country can ever do. It's not something that pays off immediately. It's something that takes 10, 20 years to come for the students to come through the education system. But eventually, these countries that have done that, like Vietnam, like Finland, like Poland, Denmark, they are coming off very strongly.
That's really inspiring. I really also agree with the part how education is really an investment into the future.
Yeah.
And Dr. Meldal, your story is inspiring, and now we would love to delve deeper into your discovery. As part of your learning module, could you help us understand what we might call the art of connection in chemistry? How simple pieces, when joined in the right way, can create something far greater than the sum of their parts.
Yeah, I'm Morten Meldal, and this is Copenhagen University. Very proud to be a professor here. It's an old university in Copenhagen. And I was awarded the Nobel Prize, you see it here, in 2022 for click chemistry. When you get a Nobel Prize, you are asked to have an opinion about everything, and I don't know everything, but I do know that chemistry is everything, and it's very important for us to learn about chemistry. In particular, the young people can store images very well, and I think it would be important to make a visual introduction to the three-dimensional world of chemistry for the young people, and use this in school without any force, but just pleasure for seeing, for getting curiosity about the chemistry world. Later on, you lose this capacity of storing images, so it's important we start early on from first grades. And then we should have research without constraints, because it's really the unexpected, novelty comes from the unexpected observations in the laboratory. You cannot make good research behind an office desk. You need to go into the laboratory with open eyes and open mind, and then find the novelty in the laboratory, in the fume hood. If you do that, you should also have no constraints, because if you have an observation which is new, you should also have the ability to follow up on that observation. So too many milestones and too many regulations for your research is not good. And therefore we should have funding of research by performance. So if you perform well, you get money for the next period. I got the Nobel Prize together with Barry Sharpless and Karin Bertozzi. They both worked on other aspects of click chemistry, Sharpless with small molecules, me with proteins, and Karin Bertozzi with the whole cells. So my real inspiration comes from the forest here on my grandparents' farm, where I was really wondering how do each tree know what is around it and how it should behave. And that's, of course, all molecules that interact. So for understanding this, understanding of chemistry is important. But the real interest came from fireworks. I went to a shop south of Copenhagen and bought a box full of explosives, took them back to the basement of my parents' house and mixed them up and made all sorts of colors, and it was very beautiful. So that was, of course, a very good experience until I made a Roman light that made a huge crater in my parents' garden, and then it was stopped with the fireworks in the basement. This is Carlsberg Laboratory, and we got a grant, big grant, to investigate quantitative organic chemistry reactions on solid support for use in combinatorial chemistry. And we would like to combine that with the diversity of peptides. Peptides are composed of, in nature, of 20 amino acids, but in chemistry, thousands of different amino acids can be used. So we would like to combine this diversity of the peptides with organic chemistry to do drug development and material science. Of course, also create STEM interest in the society, because STEM is really important for also the global challenges that we are looking at the moment. So I got the money and we started doing the research with proteins, enzymes in particular, our polymer particles that we can synthesize with very high accuracy, as you can see on the picture above, and then a lot of organic chemistry reactions that we could combine with the peptide chemistry. So one of these were the CuAAC reaction, and that CuAAC reaction came about by a serendipitous discovery. So we were trying to do something entirely different, and then it couldn't work. So we were looking into the reaction mixture, and we found that a particular compound formed every time we tried it. And we investigated what that could be, and we found this triazole, and the reaction was extremely good, could be carried out in the presence of any other chemistry. And therefore, Christian Thorne, who was a PhD student at the time in my lab, he tried this reaction out with all sorts of peptides and carbohydrates to see what is the compatibility of the reaction, and then he presented in 2001 this reaction in San Diego. So I would like today to also talk about the reaction here, the N-acylaminium reaction, which is, in my opinion, and the carbamylaminium reaction, which is, in my opinion, also a click reaction. So we built a platform in which we could do many compounds by combinatorial chemistry. So we do one reaction in each of these small wells. We can then mix all the beads and put them back in here, and we can do another reaction, a different reaction in each of these small wells. And in this way we exponentially build up a lot of different compounds. We can, with 10 reactions and 3 reaction steps, we can make 1,000 compounds. So we make typically 100,000 compounds, and then we test them with enzymes. So here you see the enzyme is active with 6 of these small microparticles here in this huge collection of compounds. So we isolate these compounds, we take them off the solid support and analyze their structure, and then we resynthesize them, and here they are injected into a mouse which has arthritis in the foot, and we can see the enzyme, exactly what enzyme is reactive when in the development of the arthritis. So this is very important, because if you want to control arthritis, maybe you want to control those enzymes that degrade our cartilage. We can also make all sorts of skeletons, and these interesting molecules looks like pharmaceuticals, so I will tell you a little bit about the reaction that leads to these scaffolds. We can also make catalysts like this is palladium bound to a peptide which is chiral, so we can make chiral catalysts out of this. We can also make molecular recognition, and here's a small peptide that was isolated out of 500,000 peptides that we made. It's made of D amino acids, so it's not natural, but it does behave very much with the cells. It adheres to the cell membrane, and therefore if we have this peptide on our small particles, we can make a monolayer of cells that grows on the surface of our beads, and they can act as a detector of the activity of the compounds that are attached to the bead. So this is what you see in this picture here. We have one active compound and a lot of inactive compounds. So we take out this one and analyze it. We have an analysis system which is by immobilizing small microparticles. We make sort of a barcode which we read every time we do something with a bead. And in this way we can have the history of the synthesis and the activity that we isolate here. We can then read what structure is on the bead. So here's an example of a bead, a microparticle with nanoparticles immobilized inside, making this matrix that we use as a barcode. So we were working with these very difficult peptides. They cannot be synthesized in any other way than this. And we were using A sites of amino acids. So this is 3 nitrogens instead of 1 on an amino acid. And then we have an acid chloride. So this is a carboxylic acid converted into a very reactive substance. So we expect this to react with that, and it does, and we can form these complex molecules. So that was a very good reaction, and I asked Christian Thornø to take an alkyne and make a copper cuprate of that alkyne by deprotonating at copper and putting the copper here at the end of the alkyne to make a nucleophile that could react with this acid chloride and make this compound. The reason we want to do that is because then we could put this into a peptide and attach things to this triple bond that could stick out from the peptide like that. But it didn't succeed. What happened instead was this. We formed the triazole, and we investigated all the data quite a lot because we got the same kind of compound every time. We found that it was this triazole that formed, and it formed very cleanly, as you can see in this chromatogram. This is simply illusion of our compound over time. And Christian, who is here, he presented this in 2001. So we were very proud to have this publication. So what is a click reaction? First of all, we need reaction heat. When two molecules react with each other and it develops a heat, that means that there's energy escaping the system, and that is what is called high enthalpy reactions. So that makes quantitative yield because as the energy escapes, it doesn't go back. And we also need orthogonal click functionalities. That means that the click should not react with all the other functionalities we have in our molecules. It should be very easy to access the click functionalities, and they should be easy to install in the molecule. They should be selective and biocompatible, and they should react cleanly at 20 degrees centigrade. They should also be both stereo and regioselective, and preferably be a triggered reaction. That means that we can add something that starts the reaction, either light or catalyst or something. It should also be insensitive to benign conditions like carbon dioxide, water and oxygen. And that's where our click reaction actually fails, because it's completely incompatible with oxygen. It should also be coordinative in the transition state. That means that when we want to perform this reaction, we should have the two components sitting on a catalyst close together so that they will actually react with each other at low concentration. And that should provide us access to otherwise inaccessible architectures of molecules. So they are very difficult to find, and only very few ones. Oh, this is actually a very good vacation, a vacation in Sweden that I can recommend to anybody. You are invited up when you get a Nobel Prize, and they're very good in Sweden of taking care of you. So this is the first day, and you deliver something that meant a lot. This here is a 20 well block that we used. This is made in the garage of my neighbor. He had a lathe that I could use, and I made this apparatus, and that allows us to do the first combinatorial libraries where we are mixing the beads in between the reactions. And that is now up at the museum together with my signature under one of the chairs from the bar. This is my signature. And yes, so I was working also on other things at the Carlsberg laboratory, and here's one reaction which we really wanted to do, which is installing what we call an aldehyde, this functionality here, at a peptide, and then use this very reactive group to react with nucleophiles. So this is an electrophile without electrons, then we come in with a nucleophile that has electrons, and they react with each other because the lack of electrons wants to be compensated with electron density that comes from the outside. So that's why this will react, and it can react in many different ways. For example, we can make first a double bond to nitrogen here, and then couple with a carbon from this moiety called an indole. We can also make a double bond between two carbon atoms out of this oxygen double bond. Or we can add an amine and reduce the double bond we get with amine to get this. And it worked well, but only when we have these groups installed on the amide bonds. The reason was that this aldehyde goes back and reacts with the amide bonds. And amides are thought to be completely inreactive in these kind of reactions. So we were very stunned by this observation. And we made a new reaction out of it, in which we take, this here is actually an aldehyde, but it's protected so that it won't react. And we can use this as a building block and incorporate it into a peptide. Then we can treat it with acid. Acid releases the aldehyde. You can see the aldehyde here. And this aldehyde then forms a reaction with the amide bond, making a very reactive so-called N-acyl iminium ion that can react with carbon in carbon nucleophiles like these endoles. So that forms this kind of heterocyclic system. And this is actually extremely useful because there are so many amino acids, so many peptides, and we can fold them up as we like in this manner and make small molecules that are interesting for pharmaceutics. So we needed to have some building blocks. We started out with what is called a malonic ester synthesis, introduced the aldehyde first in a protected form, and then we could put on a side chain here. We take off a proton and do side chain here, take off a proton and do the alkylation of these electrons that are left, and we get installment of this group here. So now we have a building block. We can also do reactions directly on this position, so we get that aldehyde, and then we can protect that if we want to. So this is a way to get a variety of different building blocks. We also have access to building blocks via alcohols, which we can differentiate the ends of diols here to get aldehydes and so on. And that gives us these kind of building blocks. And then we can take a double bond, and then we have developed a very specific quantitative reaction that works very selectively on double bonds to give us these aldehydes in situ. And we have also taken amino acids, and we have reduced the carboxylic acid to an aldehyde. We have protected it, and then we have made the other end here reactive with nucleophiles by installing a pentafluorophenyl carbonate. So we have a variety of different building blocks that we can use. We start out with these kind of building blocks here. And you can see they form first the aldehyde, and the aldehyde react here and react with the side chain. And here is 4 different compounds. And the stunning thing is the crude materials that we get out of this reaction on the solid support are extremely pure. Only one thing happens. So this is exactly what you want from a click reaction. This is the HPLCs, that means that it's chromatograms. We elute through a small column these compounds, and they stick to the column with different affinity and come out at different times. And here we see there's only a single compound in this mixture. The same with the crude NMR spectra. They are very, very clean. It's very rare you see a crude product with this cleanliness. And we could also see that we form very specifically the reaction here to give us one stereoisomer, where we have a short distance between these two. And we can see that with something called nuclear magnetic resonance, where we do a energy relaxation between these two, and that energy relaxation can be recorded, so we can see that the distance is short. So we form only one stereoisomer at this center, and that depends on the stereochemistry at this center. The reaction was tried with a variety of different nucleophiles here and electrophiles here, and you can see now on the next slide how cleanly it worked in each case. So here we have 2 stereoisomers at this center, so we get 2 peaks, but they form very cleanly. Here we have used commercial amino acids which are not chiral at this position, and you can see again we form 2 compounds, but we form these 2 compounds very cleanly. Yeah, so if we look at this is called a phenylalanine with an iodo substituent, a bromo substituent, a chloro substituent, so different halides or methyl groups, phenyl group, different groups sitting on it, and in all cases we can make this reaction work. It was not expected that we would have this reaction with 2 chlorides working, because the chlorides extract the electrons from the aromatic ring, making it much less nucleophilic to react with the electrophile at this position. But it still worked extremely well. Yeah, we jump over that. And so we can also make quite complicated structures. Here we have naphthalines and heparines that reacts with the electrophilic center here. So this is a new bond that is forming, and is forming quantitatively. You can see it here for these 3 reactions. And we're back in Stockholm, and this is a day where you present your lecture. This is a very humble situation, because you are presenting for maybe millions of people, and you are nervous initially, but then so when you get into it, it's okay. And after the lecture, both I and my 2 colleagues were very happy. So here you see the emotional moment after all lectures were finished.